tutorial I just want to look at how we go about characterizing a molecule or determining what its structure is and things like that. It's going to be a very basic introduction, so it's going to go over the shapes of molecules. I'll use a similar molecule to what I had in previous tutorials. I'll bring this one up that I've already drawn, and as you can see if you look at this, we have a cyclic ring here, and I've drawn it in 3 dimensions, or tried to draw it in 3 dimensions, and this carbon-oxygen bond here goes up, and we've got an ester group here, and I'll do a tutorial on functional groups, so you'll be able to see that in the side. Have a look to the side after this tutorial for what all the different functional groups are called. So this is a cyclic ether system, and it's got this chair shape to it as well. But imagine we did a reaction and we couldn't actually tell whether it was that one or whether it was that one, or even if this is flipped up here to give what's called a Bort conformation. Now there are lots of techniques available to actually help a chemist determine which one's which, and you've seen the mass spectrometry tutorial, I hope. If not, this is just brief. I've got a picture of it here. This is just a brief example of what it does. You put your sample into the machine, it volatilizes it, so it makes it like a gas, and then it goes into a vacuum chamber here, and then it's bombarded with particles, either electrons or other forms of particles, and then because these are charged particles, it bends. The magnets make the charged particles deflect or attract towards the magnet, so these high velocity particles are then bent on their path, and they separate out depending on the mass and which charge they have. So you end up with a spectrum, a mass spectrum, which is a result of the charge and the mass of the compound. So something like this has got a molecular weight. So molecular weight, I think it's probably written down that all like this, FW, and that's 159. So this is a molecular weight of 159, and we can determine that with the mass spectrum. We can take this sample, put it into the mass spectrometer, and out will pop, hopefully if we've done it right, a series of lines, and these lines will look something like this, and they'll get smaller and smaller, and this is 0, and this will go up to, sorry, that's not very good, that'll be 0, and let's say, well, we know it's 159, so let's say this goes up to 200 here, and this particular peak here is 159. Okay, and these will be degradation products. So if we look at this here, this could fly off because a chemist will know that this would pop off quite easily, and so on and so on, or it might break here and so on. So these would be fragments as it breaks apart in the mass spectrometer. So as it gets charged up, it will undergo its own reactions where it disintegrates basically to give little fragments. So it's a bit like dropping a cup on the floor. So this is the molecular weight of the cup, and then this will be the handle, and this will be all the other bits and pieces that have made up the cup. But instead of a cup, it's a molecule like that, and this will be a mass spectrum, and this here will be this intensity here will be determine how much of each fragment there is. So it's like a relative intensity, and this here is actually not the actual mass of the compound, but it's a mass of a charge ratio. That's the Z for charge, and that depends on how many, because some molecules can pick up more than one charge, and then this greatly affects this number. So if you've got one charge, that is basically the mass of this, and if it's got 2 charges, so if that Z is 2, it's picked up 2 charges, then that'll be halved, and so on and so on. So that's a mass spectrum. So that's very useful for determining the molecular formula, if you will. So the mass spectrum. So that's one way of looking at the compound. That's a very quick way of looking at it, although mass spectroscopists will probably say it's not a very quick way, but I'm sure it is. Okay, so that's a really useful technique, and if you're a chemist you'll definitely come across that and definitely use that technique. Another technique is, if you imagine you've got a mixture of compounds, so you took a sample, say it's from a crime scene. You know, a lot of people watch this crime programs on TV, and they take samples and they put them in the lab. Well, then sometimes you need to separate mixtures out, and we do this using chromatography, and you might do this in your school or college, where you separate compounds out either by the mass or the charge or their interaction with some surface. So if you do the blotting paper experiment, where you take a piece of blotting paper and you put some ink on it, and then you put it in some solvent, put it in a tub. That's a bit skewed, that. So you put it in some beaker with a bit of solvent in there, and the solvent rises up like that, and over time, so we draw this over time here, over time, so T in your beaker, and you've still got the solvent, and we tend to put a top on that so it's all super saturated, so the solvent doesn't evaporate too quick. It's all saturated in there, so it doesn't give any funny results. I tend to put a top on it, so I'll leave my top on. That's a top. And then over time, that spot, which was a mixture, separates out, because these compounds are slightly different and they interact with the surface of your chromatography paper, if you will. And over time you'll get these patterns or these paths from the original one spot, and this is determined by what's called the polarity of the molecules, and basically all that is the stickiness of the molecules towards this compound that they're travelling through. So that's chromatography. Now that's quite useful to do this. This particular technique that you'll do at school is called thin layer chromatography, or sometimes called TLC, thin layer chromatography. I'll put all these terms up at the side. But what you tend to do when you've got complex mixtures and you want to know accurately how much, so you want to know, so that's 10%, say, and say that one's 25% or whatever. Now, if you did thin layer chromatography, you have a rough guess based on some of the samples you might have. But if you want to really find out how much you've got, after a lot of hard work, and believe you me, it's a lot of hard work, you've got to determine what kind of response your compounds will give. So any analyst would tell you it's not that easy, but once you've got a method in place, you get something that looks very similar to, I'll just change my pen colour, you get something that's very similar to the mass spectrum we just saw. And you have compounds coming off, they'll be at what's called a lute off, and they'll come like that, and you want them to look a bit like, well, they don't look like that. Let's go back a bit, that's not very good. So they'll come off, and it's a continuous stream, and the sharper they are the better, but sometimes you get two compounds coming off very similar like that. So this is time, and this is what we call area percent. I don't know why I wrote that backwards, but that's area percent. And what an analyst will do, they'll look at the area under this peak here, and so if I just shade it, and then you can see it's not very well shaded region there. So all that area there will be basically a representation of the percentage of your compound in a mixture. And this here, we draw this in a different colour, this area here might represent another compound, and so you'll be able to say that 80%, and this will be, you can get quite accurate numbers, so this would be 11.6%, say, compound A, that's compound A, that's compound B, and so on and so on. It's not very good percentages, obviously, because this is a lot here, but basically you get the idea that you can separate compounds out from complex mixtures and then find out what ratio of these compounds are present. So that's another method, that's called chromatography. That was terrible. And that's chromatography. Okay, that's chromatography. So that's a way of separating out complex mixtures. Now, if I just get rid of this, if you wanted to look at difference between these two molecules, you could use mass spectrometry because they have different weights. This has got nitrogen rather than oxygen, so it's actually got a molecular weight of 157. This one, 157. Well, that's great. That'll tell you how many atoms you got. It won't actually tell you how they've been ordered and distributed, so that won't actually tell you the configuration of the molecule, and it won't also tell you what's called the conformation of the molecule, which is the actual shape it looks as well. So if you want to look at the molecule in more detail, then you use what's called NMR, and that's nuclear magnetic resonance. Now, of all the spectroscopic techniques, this is quite unique because it looks at the nucleus. So all the other spectroscopic techniques that you come across will actually look at what the electrons are doing, so the vibrational stretches and stuff like that. But this actually looks at the nucleus of each atom, and because they've got a special property called spin. Now, I won't go into the detail what spin is at this stage, but basically NMR in a nutshell allows us to look at individual elements which are present in our molecule. So if I just actually just get rid of this for now, clean it up a little bit. So we're concentrating on NMR. If we look at our molecule and we want to be able to determine its structure, then a very good technique would be you look at Proton Nmr. We call it proton because the nucleus of a hydrogen atom is a proton. So we'll just get a different colour. Let's have a look at all the different hydrogens. I'll call them hydrogens for this tutorial. So we've got hydrogen there, we've got hydrogen there, we've got hydrogen there, and so on. All these hydrogens are all in different environments, okay? Now, if you got rid of all the other elements and got rid of the structure, you'd still have all these hydrogens in those positions, and they can see each other in the NMR spectrum if you look at them. And so you'll be able to actually find out the position of the hydrogens in that molecule. So not only would you be able to determine, yes, you've made that molecule because the right number of hydrogens are present, but you'd also be able to say it is actually with that oxygen and this ester group going up, because this hydrogen here is seeing this one and this one. Okay, so this one's related to this one and this one's related to this one as well. And if that hydrogen was sticking up, it would probably see that one more than it would see these two. And so you can actually determine that. You can actually see which hydrogens are in actual positions in your structure. And from that you'll be able to get the three-dimensional structure of a molecule. So that's NMR basically. And you can also look at carbon, but you have to use a special isotope of carbon. You have to use carbon-13 because carbon-12, the natural abundant one, doesn't have nuclear spin. So you can actually determine which isotopes to look at as well. So it's very, very interesting technique. So that's NMR. So the last thing to have a look at your structure of your molecule that I want to talk about is infrared spectroscopy. I'll just see if I can get rid of these. Infrared spectroscopy looks more at functional groups, then, oops, I'm not going to be able to do this, am I? So infrared spectroscopy looks at the vibrations of the molecules. So this is infrared, sometimes called IR, infrared. It's called infrared because it actually uses the infrared wavelength. So very close to red colour in the spectrum. So it uses infrared. It looks at the vibrational spectrum of molecules. Now that's because if I just draw water molecules as an example, molecules aren't still, they don't keep still, they have a lot of energy, and these bonds here will be vibrating backwards and forwards. That'll be going bang 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 like that, and that'll be going the same like that. And you also get some stretching inside there, a bit like a pair of scissors opening up, and things like that. And these can stretch together, so you go boom boom boom, so as that goes down, that one goes down, or they can be what's called asymmetric stretching, and that can go down and that can go up, and so on and so on. And what that does, it actually gives you a spectrum, which you might have seen in school and things like that, which will look like this. And what these are here, what these are, and this here actually, it'll be this carbonyl group actually, and that'll be about 1700, something like that. And I've not actually told you what this is yet, but this is basically what's called the wave number. Just another way of talking about frequency, really, or energy. It's all related to the energy, really. And this will be percentage absorbance. Okay, so that's basically how much, if you fire infrared light through this, so you fire infrared light through your molecule, let's get some colours here. So you fire infrared light through your molecule like that, and if you fire it through a blank cell as well, so something that didn't have your molecule, and then look at that, and basically what you do, you compare firing the infrared through nothing to firing the infrared through this molecule. And as that infrared goes through your molecule, some of the molecule starts to absorb the energy, and so you see a difference compared to the one without the molecule. And that's what this is. This is basically your molecule absorbing the energy that's different to the one with the molecule not being present. And each vibration, each bit of energy that it absorbs, is quite unique to the functional groups of the molecule. So I put 1700 here, it could be different, but it's in the right region for this carbonyl here stretching, so you can very quickly point out that this region here is typical of water stretching and things like that. And then you've got your halides down here and your double bonds and things like that. So this infrared spectroscopy is very useful for functional groups. So that's a basic introduction to how you can characterize molecules, different techniques, and I'll put a list of those techniques and some links to other tutorials, so a bit more in depth into those techniques. But basically that's how chemists determine the structure of molecules. And I hope you enjoy this, and hope you go on to have a look at the other tutorials too.